All right, good morning. Yeah, it's time to look at solutions and what they do. I'm gonna get my notes out here. Sorry, I'm moving around. Remote. All right, so you should have the notes concerning solution traits from chapter 16. I know we don't really have the books, but that's just where it came from out of my book that I have. So the notes should look like something like that. Is what you should already have copied down, and you should have already sent to me. So ultimately, I'll quit telling you guys that because you'll be in the habit of doing that all the time. So, well, number one says types of solutions. Backing up for 1 second, what is a solution? A solution is a mixture. And if you remember a mixture, the stuff that's inside there keeps all of its original properties. It hasn't changed into anything new. It was not a chemical reaction. Right? It's not chemical properties. So it didn't change into something new. Everything that's in it maintains its original properties. And the one we talked about in the notes was Kool-Aid. And in Kool-Aid, we have water, which makes it a liquid. We have sugar, which makes it sweet. Then we have food coloring, which gives it a color, so like red. And then we put flavoring in it, which makes it taste like cherry. So all four of those things are inside that jug of Kool-Aid. Right? And all four of them maintain their original properties. All right. So it's just a physical mixture. So, all right. Number one, types of solutions. It says letter A. You can have a solution with two liquids. Vinegar is actually two liquids. I know you're like, no, it's not. It's just one jug. It's got liquid in it. It's vinegar. No, the reality is it's actually water, and then it has a really, really small amount of an acid called acetic acid, and it ends up becoming a 2% solution of acetic acid. So it's really a mixture of water and acetic acid. If you had really concentrated acetic acid, it's really, really, really strong. It'll take your breath away. It's really nasty stuff to work with. But when we dilute it way down and make it 2%, it's vinegar and we can eat it. So another one, you can have a liquid with a solid. That's Kool-Aid. Kool-Aid, solid, that's the water and the sugar, and they mix it together. It makes a solution. We can have a gas and a liquid. That's like the carbon dioxide. That's in pop. That makes it go when you open it up. We can also have two solids that are mixed together as a solution. Two solids, that's crazy. Like brass. And brass would be like, we buy light fixtures that look like brass. You can buy door handles that look like brass. It's kind of a golden color. And that's actually copper and zinc that they mix together as a liquid. When it's all heated up, they mix it all together, make it into a solution, it becomes brass. And then they spray it onto the object that they want to look brass. And you end up with this brass colored light fixture or brass colored door handle. So, or you can actually even buy things that are entirely brass all the way through. So those are all examples of solutions. Remember that in our other notes also we said solutions. I always like to say they are clear. And one reason for that is because they're basically the same throughout, all the way through. So, all right, well, things that affect that solution formation. This is number two, letter A. Number one is agitation. Agitation, that's not being mad in this case. This is the idea of stirring something. If you agitate it, it means you stir it up. If you stir something, what it does, it increases the rate, how fast something dissolves. It does not make it so that it will hold more. And that's what it says underneath, does not increase the amount that will dissolve. It only increases contact with the particles, solute and solvent. Makes it so that they come in contact more, therefore it will dissolve faster. So if you're trying to make Kool-Aid, right, what you can actually do, when you put the water in, then you pour the sugar in, you could actually just take it after you pour that in, just put it in the refrigerator, just leave it. It will actually mix all by itself. Because the water that's in there is moving all over the place, and it will slowly make contact with the sugar, and the sugar will get dissolved. It's probably going to take 2 days, maybe even 3 days before it'll finally entirely be dissolved. Well, we go, man, I don't want to wait 3 days to have a glass of Kool-Aid. I want it right now. So what are we going to do? Well, we stir it up. And when we stir it, we speed up that process and get that stuff to dissolve faster. Right? But again, stirring it doesn't mean that you can add 5 cups of sugar to it and get it to all that 5 cups to dissolve. It won't. It will only hold a very specific amount. And really what's happening in this is, if these are my water molecules that are inside that jug of Kool-Aid, so each one of these is some H2O, right? Well, in that water, there's actually little spaces right here where there's nothing at, right? And what we're trying to do is we're trying to get that sugar that's down here on the bottom. So this is the sugar. We're trying to get that sugar to go in here and fill in these spots. Right? That's what we want to happen. And again, it will do it all by itself because these particles, the water particles, are moving around, and that sugar will slowly get up in there. But if I want it to come in contact faster, then I stir it up, and I can get the sugar up here, and then plink, 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 and it drops into those spots, and it'll dissolve faster if we do it that way. Right? Letter B, temperature. If I raise the temperature on it, that increases the kinetic energy. Right, makes these water molecules move faster. What kind of goes along with the idea of agitation or stirring. So I raise the temperature, they move faster. If I make them move faster, then that can have an effect upon getting these solid particles to get up in here inside those spots. Now, when you do temperature, there's two different effects that occur. So we have to look at the idea of a solid, like the idea of sugar. It's a solid, trying to get a solid to dissolve. And if you do that, increasing temperature will make it increase solubility, will make it actually hold more, right? And what it really does is, because we make these things move faster, they actually do this and they pull apart just a little bit. And when they pull apart, these little openings in here actually get a little bit bigger. And if they get a little bit bigger, then they can actually get more stuff in there, right? It makes it easier to get the stuff in. So we can actually increase solubility by increasing temperature. Oh, think about the idea, and we're getting into cold weather. If you make some hot chocolate, and if you have the little packets I have at home where you like tear the top off, pour it into a coffee cup, and then you pour hot water over the top. Number one is, in order to get that stuff to dissolve, you usually have to stir it. And if you stir it, that gets it all to come up there and get inside those little spaces. The other thing is if you take that hot chocolate after it's all mixed up, and for some reason you forget to drink it, so it's sitting on the counter, right? And all of a sudden it gets cool, and it cools down. What do you notice at the bottom of the coffee cup for your hot chocolate? Well, you're going to notice there's a whole bunch of stuff down at the bottom of the coffee cup that fell out of solution. It fell out of these pockets. Why did it fall out? Because it was hot at first, so it was pulled apart. As it cooled, they come closer together, and there's smaller spaces, and it falls to the bottom. And you end up with that powder that now is like mud in the bottom. And if you stir that, you can stir it all you want. When it's cold, you'll never get it to dissolve because those holes aren't big enough. The only way you're going to get it to dissolve, heat it back up, open it up a little bit so the pockets are bigger so that you can get that hot chocolate particles in there again. All right. So in the case of a solid, raising a temperature raises the solubility. Now in the reverse of this, if we have a gas and we put a gas in a liquid, so let's use the idea of pop. And in the pop, the gas that's present in that is carbon dioxide. So let's say you take a pop and you go to Walmart and you take this brand new bottle of pop and you set it on the dashboard of your car and you go into Walmart and you go shopping for 2 hours. Right? And you're in there for 2 hours. It's a beautiful sunny day. It's really, really hot out. What's going to happen to the temperature of that pop sitting on the dashboard of your car? It's going to get really hot. Right? You come back out and you grab a hold of that pop bottle and you're like, oh my word, this pop bottle is like really, really firm. It doesn't squeeze very much, even though the lid's on. And then if you take that thing and you pop it open, what happens? If you've ever done this, all of a sudden you're not going to look very good afterwards because it's going to go all over the place. Okay? And you're going to end up losing all of that carbon dioxide. And then you try and drink the pop. Besides the idea of it being hot, it's going to be flat because you just lost all that carbon dioxide. By increasing the temperature of a liquid, it actually makes it so it cannot hold the gas. And the gas will actually leave that pop. And you'll lose the gas. It won't be able to stay inside these little pockets anymore. It actually loses it. So if you had a pop bottle that was on the dashboard, it was really, really hot, how would you get that gas to go back into the bottle before you open it? And once you open it, it's all over. Well, what you could do is take that hot bottle of pop, take it home, put it inside the refrigerator, cool it down. If you cool it down, then the gas will go back into the solution, and you'll still have a bottle of pop that's got carbon dioxide in it. All right, but again, if you open it, let all that carbon dioxide out into the air, it's gone, and you aren't going to get it back in there. All right, so gases raise the temperature, solubility goes down. It lowers that solubility. All right, the opposite of a solid. Sugar or solids raise the temperature, more of it can go in. Gases raise the temperature, solubility goes down. One issue that can happen on this is a thing called thermal pollution. In the case of thermal pollution, what it is that if you have a river, right, and if a factory, which used to be a real common thing, they still do this, but they'll use water to cool down a machine. And when they do that, the water actually warms up. What factories used to be able to do is they would take that warm water and, well, what do we do with it? Okay, well, we'll dump it in the local stream and it'll cool down out in the environment. But when they would do that, dump it into the stream, it would warm up the stream. As it warms up the stream, then the solubility of the gases in that water goes down. And one gas that's very, very important in a stream, oxygen. You got to have oxygen in a stream. If you don't have it there, what happens to the living organisms, the fish in the stream? If there's no oxygen in the water, they're all going to die. That's why if you have a fish tank at home, you have a little bubbler going inside the fish tank, and what's that doing? It's putting oxygen into the water so that your fish stay alive. Well, same thing in the case of a stream is we want to make sure that that water has oxygen. You raise that temperature, oxygen level goes down, and all of a sudden we have all sorts of dead fish along the side of the stream. They didn't die because they got poisoned. No, they actually suffocated in the water. That seems really crazy. They drowned. How in the world does a fish drown? Well, they drown because there's no oxygen in the water. Because they're raising that temperature, it lowered the oxygen level. That's called thermal pollution. Right? It's a pollution because the water that was put in there was too hot. Currently now, that process is illegal. Businesses can't do that anymore. They actually have to take that warm water, put it into a pool, let it cool down, get it to normal temperature. Then they can actually pour it into a local river after it's been cooled back down. Usually what they'll do is they'll cool it down, then they'll run it right back through the system and warm it back up to take the heat away from the machine, put it in the pool, let it cool back down, run it back around. And they just keep doing that over and over and over instead of sticking it out into the environment. All right. Another one, particle size. We're going to do this one, then I'm going to move on to video number 2. Particle size is small dissolves faster than large. All right, if you go back to that idea of the hot chocolate. A hot chocolate packet, when you pour it out, it should be all little bitty particles. By being little bitty particles, makes it fit into these little spots a whole lot easier. Then if you have an old packet of hot chocolate that was in the cabinet from last year, and you tear it off and open it up, it's one big chunk. Just because it's been sitting for a while, you pour that big chunk in there, it takes a lot longer for that big chunk to dissolve because the inside of that chunk down here doesn't come in contact with that until the outside pieces are gone. Right, so if we can powderize things, it makes things dissolve faster. If you think about the things that we try and make solutions out of, Kool-Aid, it's a powder. Instant coffee, it's a powder. Gatorade, it's a powder. If you had like the powdered stuff to make Gatorade out of, we make them all in powders. We don't make them into big old chunks. And after big old chunks, it's going to take a long time to get that stuff to dissolve. So the whole idea on that, part B, is there's more surface area to contact the solute and solvent. The solvent can get in between that big chunk and make it so it can come in contact with it, and more of it will dissolve a whole lot faster. I'm going to stop there for right now. You're going to go on and watch video number 2. All right, video number 2 will hopefully finish up these notes.